Today, on the last day of our unit, we're going to classify collisions. Now, there's lots of ways in which we could classify collisions. We could classify them as one-dimensional or two-dimensional. We could classify them as head-on collisions or rear-end collisions. But we're going to classify them today in an entirely different way. We're going to classify them today not based on momentum, but rather based on kinetic energy. The first type of collision that we have is called an elastic collision. An elastic collision is a collision in which momentum, of course momentum is conserved. Momentum is always conserved if we have an isolated system. If there's no external forces, momentum will always be conserved. That's not what I want to draw attention to today. I want to draw attention to the kinetic energy. Kinetic energy is conserved. In other words, kinetic energy isn't lost. The amount of kinetic energy we have after the collision would be the same as the amount of kinetic energy that we have before the collision. That's an elastic collision. Now, the other kind of collision we have is called an inelastic collision. It's a collision in which, well, momentum is still conserved because as long as we have an isolated system, momentum is always conserved. But this time, kinetic energy is not conserved. In other words, kinetic energy will be lost. You have less kinetic energy after than you have before. Now, someone in the last class asked a good question. Is it ever possible to get more kinetic energy afterwards? Is it ever possible to gain kinetic energy? Well, in an explosion, yes. But we're not classifying explosions here. In a collision, you have to have either kinetic energy staying the same or you have to lose kinetic energy. One of the two. Now, if you lose kinetic energy, where do you think it's going to go? What type of energy does it go off as? Yeah? Yeah. Heat, yeah, good. Usually going to be heat, but you could lose a little bit due to sound as well. Sometimes the kinetic energy stays the same. It's elastic. You don't lose any. But sometimes, lots of times, you do lose kinetic energy. But it's never destroyed. You know that energy can't be destroyed. It has to be transformed into something else. And if it is transformed into something else, it'll be mostly heat, maybe some sound. Here's a couple little things that I want you to watch out for. If it's a collision in which the two objects stick together, automatically we know it is inelastic. Always. If the two objects stick together, they entangle, they head off as one, kinetic energy will always be lost. You don't even need to do a calculation here. You know 100% for sure the kinetic energy will be lost. No, the energy stays the same, but it's just you lose a little bit due to of kinetic energy. It's transformed into something else. Now, if they bounce apart, which a lot of collisions do, then it could be elastic, but not necessarily. Because it could be inelastic as well. We don't really know. If they bounce apart, it could be either one. We have to do a calculation to figure out which it is. And we'll show you an example of that in a couple minutes here. Stick together, always inelastic. Bounce apart, don't know. Got to do a calculation. Now remember this as well. I want you to be able to determine with 100% certainty whether it's elastic or inelastic. But if you can't, if you're just not sure, if in doubt, you should guess, make an educated guess, inelastic. And the reason you should guess inelastic is because 90% of the time collisions will be inelastic. Maybe even higher percentage than that. You very rarely actually get an elastic collision. So if you're going to guess what it's going to be most of the time. You could be wrong with that guess, but at least your odds are pretty good. Now let me explain briefly why most collisions are inelastic. You guys might remember this from Science 10, maybe. Second law of thermodynamics. Lots of different ways of stating that, but the way that you learned in Science 10 was every time you have an energy conversion, you always lose a little bit. Do you remember that? When you have an energy conversion, you always lose a little bit of energy. Picture a basketball bouncing on the floor here. That's a collision, right? What kind of energy does the basketball have just before it collides? Just before it collides, it's all kinetic, right? Just before it collides with the ground, it's all kinetic. Now, as it collides, the basketball squishes, right? So we're converting kinetic energy to elastic potential. And then as the basketball goes back up into the air, the ball goes back to its regular shape where elastic potential energy is being converted back to kinetic. So we had two conversions there, kinetic to elastic potential to kinetic. Second law of thermodynamics says anytime we convert energy, we always lose a little bit, right? So we can't have as much kinetic energy at the end as we started with because we had an energy conversion. The only time you have elastic collisions is when things that don't squish hit each other. Two marbles hit each other, that would be pretty close to elastic because they don't squish very much. Subatomic particles hit each other, they don't squish at all. So that would be an elastic collision. That make sense? That's why most times it's inelastic. But I'll tell you, if they bounce apart, even if you think it's going to be inelastic, you got to do a calculation. But if you just can't figure it out, guess inelastic because most times it will be. Okay, we've got a couple examples for you. First question says a 2,000 kilogram truck traveling north at 20 collides with a 1,500 kilogram car traveling south at 12. They entangle and they head off together at 6.28. Elastic or inelastic? Quick answer, quick. What is it? How do you know it's inelastic? Because they stick together, yeah. You don't have to do a calculation here. We know it's inelastic. We know kinetic energy will be lost. How much kinetic energy is lost? I don't know. But we know there's going to be some lost. We know it's going to be inelastic. 100% certainty. Because they stick together. Second question, not quite so easy. Second question, they don't stick together. They bounce apart. 5 kilogram ball traveling east collides with a 6 kilogram stationary ball. After the collision, the 5 goes off at 0.6 at 50 degrees north of east. The heavier one goes off at 38 degrees south of east. Elastic or inelastic. They bounce apart. Bounce apart could be elastic, could be inelastic. If you had to guess, what would you guess? I'd guess inelastic if I had to guess. But let's do the math here and just check this. Okay, this is a kinetic energy problem here. We're trying to find out whether it's elastic or inelastic. So calculate the initial kinetic energy. Now, notice what I'm doing here. I am not paying attention to the fact that there's a funny angle. I am not doing X and Y components. Why not? Why am I not doing the funny angle? Why am I not doing X and Y components here? Because kinetic energy is a scalar. Perfect answer. It's a scalar. If I was using momentum for this, which if I didn't know what the final velocity was, I'd have to use momentum, then I got to pay attention to vectors, the vector nature of it. But for kinetic energy, I don't. 1/2 of 5 times 0.98 meters per second squared plus, well, the second one's at rest, so its kinetic energy is 0. I do the math there, I get 2.4 joules. To 2 digits, 2.4 joules. Let's find the final kinetic energy. What do we got here? The lighter one goes off at 0.6. And the heavier one goes off at 0.63. Solve that when it works out to be 2.1, 2 digits. Look, guys, 0.6 at 50 degrees north of east, who cares? Kinetic energy is a scalar. 0.63, who cares? Kinetic energy is a scalar. Momentum, sure, it matters. Kinetic energy doesn't matter because it's a scalar. Okay, elastic or inelastic? How do you know? Yeah, since kinetic energy is lost, it's inelastic. Somebody in the last class asked a good question. Said, what if, like the sig figs, like how many digits should you round it to? Like, what if it's really, really close? Like what if you had 2.403 and you had 2.401? In this question, we would say elastic because to two significant figures, they'd both be 2.4. Does that make sense? The right number of significant digits, is it the same number? Right? No, because that's a good question, though. Technically, wouldn't it be inelastic because you're losing kinetic energy? The idea of significant figures is that these digits here are uncertain. So even though this one's slightly more, we can't really say that it actually is more because we're uncertain about what those numbers should be. Okay. The whole reason that we round to significant digits is to show our degree of confidence with our answer. We're only confident to 2 digits here. So if we're not confident to 4 digits, then 0.03, 0.04, 0.02, maybe they're both 0.02. We just don't know, right? So if they're not significant digits, we can't look at them, and we can't say technically it would be inelastic. It's 2 digits. It's elastic. Okay. Your homework. Oh, just in time. Good news though, I'm not going to give you the worksheet on this for homework worksheet number 5. All I'm going to do is ask you to look at practice question set number 6, which I believe entails like three fairly quick questions. All right.